In this video, we're going to discuss the change of basis problems. Here's the problem. Suppose we got a vector v in a finite dimensional vector space, capital V, and we know that the coordinates of v with respect to a given basis b. So suppose we know that. Okay. Now we want to find out the coordinates with respect to a different basis. Is there an efficient way of doing this? We'll illustrate it with an example in a two-dimensional vector space, but you'll be able to see how it could be generalized to higher dimensions. Okay. So suppose I have two bases for my vector space V. The first one is u1, u2, and the second one is w1, w2. The prime here is just alternate b, right? There's one basis and another basis. They're called b and b prime. Now, we're given that we know that v, this little vector, little v, can be written as a u1 plus b u2. That is the components or the coordinates of v with respect to u1 and u2 are a and b. Right? We want to find c and d so that they would be the components in terms of w1 and w2, so that v would also equal c times w1 plus d times w2. These are not dot products. They are just multiplying, scalar multiplication there. That is, in other words, we know the component vector of v with respect to basis b is ab, and we want to find the component vector of v with respect to b prime to be c and d. What are c and d? Well, if we happen to know how to write the elements of our first basis in terms of the second basis, then that really helps us along here. Notice, if we know that u1 is, and I'm using some fancy subscripts here, the k's are my constants that I'm multiplying by w1 and w2, and I'm using double subscripts because I'm going to do it twice. I'm going to do it for u1 and u2. So the first subscript is just saying, hey, this is the subscript, this is the coefficient for u1, that's also the coefficient for u1, and down here, this k2 something is because I'm doing u2. So the first subscript references which of the u's you're talking about, and the second subscript represents which of the w's. So k11 is the coefficient for u1 in the direction of w1. Likewise, k12 is the coefficient of u1 with respect to w2. And down here, k21 is the component of u2 with respect to w1, and k22 is the component of u2 in the direction of w2. Okay. So written this way, or written in terms of component vectors, that is to say that u1 is k11 w1 plus k12 w2 is the same as saying that the component vector of u1 with respect to the basis b prime is k11 k12. Likewise here, the component vector of u2 with respect to b prime is k21 k22. Now, I can substitute this in to this equation here. I'm given this, and now I know what u1 and u2 are in terms of w1 and w2. So we get a times, I can see as I was typing this in, I was using dots when I shouldn't have. These are not dot products. I'm going to just change it so it looks better. Hang on. Yeah, that looks better. So a times this plus b times that, that's au1 plus b u2, and then distribute the a in and the b in, and I get, I also rearrange some things. So the stuff with the w1s I wrote first, and then the stuff with the w2s I wrote second. So I distributed the a and the b and commuted some things around. I wrote them in this order so that I can factor out the w1 from these, and I can factor out the w2 from those. Now, I didn't say what vector space I'm in. I just said I'm in a two-dimensional vector space. You can be thinking R2 if you want, but it doesn't matter. The thing is, once you actually convert to the component forms, you're in R2 anyway. So, but all the algebra works the same, right? Distributed properties, commutative properties, things like that, because all vector spaces have these properties. So anyway, what I've gotten to is I've gotten to a point where I have V written as a linear combination of W1 and W2, which is exactly what I wanted. And so now I can see that the C value that I wanted is right here and D is right there. So I have two equations which I can think of as a system. I'm trying to solve for C and D, and here's how it's calculated. Take the matrix given right here, K11, K21, K12, K22, and multiply it by AB, written as a column vector, right, or a column matrix. Notice that the columns of this matrix are in fact the component vectors of U1 and U2 with respect to B prime, right? So this first column was U1, the components with respect to B prime, and the second column is U2, the components with respect to B prime. If you're in a bigger system, you would have had, a bigger dimensional space, right, rather than two-dimensional. You'd have had U1, U2, U3, you'd have W1, W2, W3. And you'd have a bigger system here, but it would still boil down to a matrix times the components that you started with, right? And you're going to components that you're ending with. What we're doing here is we're changing basis. We're saying here's the components of a vector with respect to one basis, here's the components with respect to the other basis. In order to get there, you just have to multiply by an appropriate matrix. And what is that matrix? Well, the theorem is this, okay? To convert coordinates with respect to basis B to coordinates with respect to B prime, so B is going to be what I would call the old basis, and B prime is the new basis that I'm trying to get to. We write the vectors as columns and multiply by matrix A, where the columns of A are the vectors of B written with respect to B prime, right? So these are the vectors of B, but they're written in their component form for B prime. Okay. The textbook says you want the vectors of the old basis written as components of the new basis. Okay. Now, I'm going to slide this up a little bit because I've got a problem with this. It's true, I understand. But the thing is, we were trying to write, we got this vector V that we know the components with respect to basis B, right? We're trying to write components with respect to B prime. So what do I need to know in order to do that? Well, I need to take my basis vectors from B and have them written in terms of B prime. It's like, well, isn't that just the same problem? Because with respect to basis B, the two, let's go back up here to basis B, right? With respect to basis B, U1 is really easy. It's 1, 0. It's 1 times U1 plus 0 times U2. And U2 is really easy because it's 0 times 1. It's 0 times U1 plus 0 times U2. So with respect to basis B, I can easily write down the coefficients for U1 and U2. I can write B with respect to B. But how do I do it with respect to B prime? Isn't that the whole problem that we're trying to find here? I'd have to multiply by some matrix. Which matrix? Well, you see the problem? We're replacing one. We're replacing the problem of finding one vector in terms of basis B prime with the problem of finding two vectors with respect to B prime. Or if it was a higher dimensional, more than two vectors, right? And so how are we actually gaining anything here? Well, to see how to do that, stay tuned for the next video.